Hi, in this video we are going to talk about overview of sorting algorithms. Sorting is one of the most fundamental problems in computer science. It's used as a prerequisite in many algorithms. So there exist many sorting algorithms, and in this video we are going to cover an overview of most of these algorithms. Let's first talk about simple sorting problem. We are given a binary array or an array of two types of elements. We need to sort it. We have talked about this problem in a separate video, and this problem is solved using partition algorithm of quicksort. So it's efficiently solvable using partition algorithm, quicksort. And partition algorithms of quicksort are Lomuto, Hoover, and naive also is there. The advantage of naive is it's stable. Lomuto is slower than Hoover. Both of them are faster than naive because naive requires extra space, but naive is stable. Let us now talk about next problem. We have an array with three possible values. For example, sorting an array of zeros, ones and twos, or sorting an array around a range, or you have an array where elements occur multiple times and you want to put all occurrences of an element together and you want to put all the smaller values on left of it or right of it. So all these problems are sorting an array with three types of values. We have a separate video with detailed explanation of this problem. You may refer that video for more details. This problem can again be solved using quicksort partition algorithms. We can either use naive partition or Lomuto partition or Hoover's partition. Naive is stable, Hoover's is fastest. Let us now talk about the next problem where you have an array of size n and range of these values is small. For example, if you have an array of size 1000 and values in this array are range from 100 to 200 only. So you want to sort such an array. For such problems, we have an algorithm called counting sort. Counting sort sorts an array of size n in big O of n time under the assumption that all the values are in a small range. So if your range of values is having k values total, for example, if the range is from 100 to 200, you have total 100 possible values, so k is 100. So this counting sorts takes big O of k time, k extra space, and big O of n plus k time. This is the time complexity and extra space requirement of counting sort. Counting sort is a good algorithm when your range is really small. Consider small ranged items, but range is slightly bigger. For example, range is n square or n cube. Say you have 10,000 elements and your range is from 0 to 1 lakh, right? So counting sort in this case is going to take 1 lakh extra space and 10,000 plus 1 lakh extra time to run this algorithm, right? For such scenarios, we have better sorting algorithm. There is another sorting algorithm called radix sort. Radix sort sorts an array where range is from 0 to n square or 0 to n cube, or the total range is size is n square or n cube. This also sorts your array in big O of n time and big O of n extra space. So this is a better algorithm when you have slightly higher range. The next problem is you have an array where data is uniformly distributed across a range. So you might be having a small range or a big range, but your data is uniformly distributed. For example, if your range is floating point numbers 0.0 to 1.0, say range is this, and you have thousands of elements, which are uniformly distributed in this range, right? What it means is you have 100 elements from 0.0 to 0.1 and 100 elements from 0.1 to 0.2. So if that is the case, you can use bucket sort. Bucket sort is the algorithm which is used when your data is uniformly distributed. You can use bucket sort to sort such an array in linear time on average. So for uniformly distributed data, we can use bucket sort, which is fastest of all the sorting algorithms for this particular case. Let us now talk about next point. When memory writes are costly. When memory writes are costly, you have two choices. There are two algorithms which can be used to optimize the memory writes. Memory writes can be costly in cases where every write reduces age of your memory. For example, EEPROM. For such cases, we have two algorithms, selection sort and cycle sort. Selection sort is a popular simple algorithm, very simple algorithm that does minimum number of swaps compared to other standard algorithms like insertion sort, quick sort, merge sort, and worst case time complexity of selection sort is n square. So it does minimum swaps compared to other standard algorithms but takes more time than many other algorithms. There is another algorithm, cycle sort, which is also worst case n square, but it is optimal in terms of memory writes. It is even better than selection sort, right? So selection sort is good compared to other standard algorithms, but cycle sort is optimal. We have discussed cycle sort in a separate video. It's the optimal algorithm in terms of memory writes. Let us now talk about next problem. Suppose in a special situation, you are allowed to swap only adjacent elements. In that particular case, in that particular situation, you can use bubble sort. Bubble sort is a sorting algorithm that swaps only adjacent items. There is an optimized version of bubble sort that works better in general compared to bubble sort, and that sorting algorithm is called cocktail sort. Cocktail sort is simply an optimized version of bubble sort. Bubble sort travels from left to right, cocktail sort travels from both the sides. The next special case is when your array is small, when you have a small number of elements to sort. For such cases, we have two algorithms, two general purpose algorithms, selection sort and insertion sort. And among these two, insertion sort works best. Insertion sort is considered the best algorithm when you want to sort small number of elements, say only 10 or 20 elements, right? And most of the standard algorithms, standard library implementations, general purpose library implementations, they switch to insertion sort when the number of elements are really small. So we have insertion sort for this case when the number of elements are really small. Let us now talk about the last point. When available extra memory is small, you have an array to sort and you want to sort it within an embedded system, or maybe you are programming in kernel for a small device. Many standard algorithms like quicksort, merge sort, they need extra space. Quicksort needs extra space for recursion calls, merge sort needs extra space for recursion calls and for merging, right? Although there are versions of merge sort which can be optimized and which can be done in place, but if you talk about typical implementation, merge sort needs extra space. And even when there are optimized versions, your optimized merge versions, you need extra space for recursive calls in both quicksort and merge sort. Although that extra space is only log n, that can be optimized to log n. In quicksort and merge sort, it's anyways log n. But they need extra space, and they need extra space especially for function call stack or maybe your user created stack. So in situations where you do not want extra space at all, when you have very small amount of memory available, there is an algorithm for this purpose called shell sort. Shell sort is a sorting algorithm which does not use extra memory. So you can say now there are other algorithms as well, insertion sort, selection sort, they also do not use extra memory. So shell sort is better in terms of time compared to them. It takes n log square n time, right? Or you can say big O of n into log n square. So this much is the time taken by shell sort. This is the optimal implementation. The simple implementation is n square in worst case, but it can be optimized to work in this time. So this is the best algorithm with big O of one express space and this much time when you have very small memory to work upon. We have talked about special cases. Let's now talk about general purpose sorting algorithms. The algorithms which are used in library functions, because library functions can be used to sort any type of array. When you talk about sorting algorithms and you say general purpose, where you do not know the range of input or you do not know anything about the data, it can be mathematically proven that we cannot sort random data in time complexity better than n log n time. So you need at least n log n comparisons to sort a random array where you do not know anything about it, right? And you have n log n algorithms like merge sort, heap sort, quick sort. These two in particular are n log n even in worst case. Quick sort is n square in worst case, but works better than merge sort and heap sort on average. So these sorting algorithms are general purpose algorithms because they three are fastest of other sorting algorithms that we discussed for special purpose, and they take n log n time. In general, if you compare these three algorithms, quick sort is the fastest of them all, right? And merge sort has this special thing that it works well for some special cases, like it's a stable sort algorithm. One thing, heap sort is not stable, quick sort is not stable by default. So merge sort is stable and it works really great for linked lists. Heap sort in particular cannot even be simply modified to work for linked lists because it needs random access. Although quick sort also needs random access, but it can work on linked lists with the same time complexity. But heap sort is not possible to work with the same time complexity in extra space. Merge sort, when you talk about linked list, the extra space requirements of merge function simply reduce to big O of 1 by using simple algorithm of merge sort. So it well suits for linked list, it's a stable sort, and it also works good when you have data on tape drive which can be accessed only sequential way, or a general purpose external sorting algorithm. It is also well suited for external sorting. One more good thing about these two sorting algorithms is they both are divide and conquer. This one and this one. They both are divide and conquer. So they parallelize really well. You can reduce the time complexity further by parallelizing these algorithms. There have been implementations like merge sort which are log square n when you have parallel machines to do the sorting, and log n parallel implementations of quick sort. Since they are divide and conquer, they are really well suited for parallel sorting as well. Let us quickly talk about hybrid sorting also. Most of the library functions, they use a hybrid sorting algorithm. A sorting algorithm which is a mix of 2 or 3 basic sorting algorithms. For example, timsort in Python. It's a mix of insertion sort and merge sort. It uses merge sort for general input, and if your input is small or it becomes small in the recursive calls, it switches to insertion sort. Intro sort, it's a mix of or hybrid of quick sort, heap sort and insertion sort, 3 sorting algorithms. In general, it uses quick sort. And when your quick sort is doing many unfair partitionings and the number of recursion calls are going beyond log n, it switches to heap sort. And when the array size becomes small, it switches to insertion sort. So it's a mix of 3 sorting algorithms, and insertion sort is used in C++ library. Many languages also have another function for stable sorting, because quick sort is not stable in general if they are using quick sort. So there is a general purpose function also called stable sort. For example, C++ has a function stable underscore sort. This function is typically implemented using merge sort because merge sort is a stable sorting algorithm.